Welcome, everyone. For today's prep, we're going to start looking at chain rule. And this is probably one of our most important derivative rules. So we're actually going to break this down into kind of three separate learning outcomes here. So we're going to see how to calculate ultimately we're going to see how to calculate the derivative of a composite function. But we're going to do this in kind of specific cases. So we're going to calculate the derivative of a composite power function. We'll see how to do that. We'll see how to calculate the derivative of a composite trigonometric function or inverse trig function. And then we'll also see for composite exponential or log functions. So all of these are just kind of special cases of ultimately what we'll see as the chain rule. So in all of these learning outcomes, we're using this word composite function or composition. And let's just remember, we've looked at this definition before. We've done a little bit of work with this. But this is just another way to kind of algebraically combine two functions. So we have our standard addition and subtraction and multiplication and division. Those are kind of standard operations. But there's another way. And so if we have two functions, f and u, we can combine them to form the composition. Composition's a brand new function, so we just kind of give it a new name. So we could think of this as just h of x, or if we want to be really fancy, we can use this f composed with u notation. But the way you calculate a composition is you start with x, and then you plug it into the inner function, what we call the inner function, and then you take that result and you plug it into what we call the outer function. So you want to think of this composition, there's kind of two pieces to it. There's the outer function or the inner function piece, and then there's the outer function. So the inner function is what do we plug x into first? That's the inner function. And then the outer function is, well, what kind of happens last? What do you plug into last? And so we're going to see how to differentiate things like this, where there's an inner function and that's being plugged into an outer function. And we've seen this idea of composition before, and a way to kind of picture this is you almost want to picture composition as an assembly line, where you start with your input. So we start with our input x, and then that gets plugged into our inner function. So the inner function is kind of the thing that happens first. And then that result goes through our outer function, and we end up with the composition. So this is ultimately the output over here. So we can think of this as an assembly line where we first go through the outer function, then we first go through the inner function, then we go through the outer function. And we can also just view this as just one process. And this is where we could use that f composed with u notation. So one way we're kind of seeing all the inner workings of this composition, and then the other way we're kind of viewing this is just taking the input and what do we get out. All right, so it's a little bit of the theory here, but let's look at a couple of concrete examples. So let's look at example 1. And we're going to work with this composition just to get a little more practice with this, because it's not like regular addition and subtraction and multiplication and division. It's a little bit different. So we've got two functions here. F of x, which is equal to the secant function, and u of x is equal to x cubed. All right, so we want to calculate, in the first part, we want to calculate the composition f composed with u of x. So our inner function here is u. And then we'll take that result and plug it into f. So let's start with the inner function. So what is u of x? Well, let's just replace that with what we know u of x actually is. It's x cubed. Okay. So far we've just replace that u of x with x cubed. So that's the first thing that's happening to x. We plug x in, and it's getting cubed. So then we'll take this result, and we're going to plug that into the secant function. So wherever we see an x here in our secant function, we're going to change that to an x cubed. So this composition would be secant of x cubed. That would be our formula here. All right, so the thing with kind of assembly lines is if you start moving around the different order of things, you expect to get different results, and that's true with composition. So in the second part here, we're just going to reverse the order. We're going to plug into function f first. So, well, what is function f of x? Well, it's the secant function, so let's replace that. So we're plugging the secant function now, the output of that secant function, into this function u. And what do we get in this case? Well, let's go up to our function u, and wherever we see an x, let's replace that with secant x. So we end up with parentheses secant x cubed. And we can write it like this, but a common way to write powers of trig functions is to actually put the exponent on the actual name of the function. So we write it as secant cubed x. But really what that means is this, secant of x cubed. So this way is actually a little nicer for kind of going to help us remember chain rule, but this is kind of the more standard way to write it. All right, so this is going to be kind of helpful, being able to take two functions and figure out their composition. But it's also going to be helpful to kind of go the other way and take a composite function and kind of break it apart into the two simpler functions. So we're going to start with parts 1 and 2 here. So part 1, we have this function h of x, and it's the function x raised to the power 4 plus 9x plus 3, all raised to the power 8. So when we're looking for the two smaller functions, or two simpler functions, you kind of want to start with what's happening on the outside. What's kind of on the outer ring of our function here? And in this case, it's this raised to the power 8. And the inner function is all the stuff that's happening inside of there. So an indication of what you should take for the inner function is if you see parentheses, the inner function should be all the stuff inside the parentheses. All right, so we'll call our outer function f of u, and we'll call our inner function u of x. So we have our outer, and we have our inner. So let's start with our inner function. That's going to be all the stuff inside the parentheses here. So it'll be x raised to the 4th plus 9x plus 3. And then our outer function is going to be, so imagine just kind of taking all that stuff that's inside the parentheses, and we're just going to collapse it down to a single variable. So imagine we're just taking all of this, and we're just going to rename all of that u. And that's what we did. So we're just renaming all of this u. And when we do that, we're going to have u raised to the power 8. Okay. What about the next one? H of x equal to sine of x to the 4th plus 9x plus 3. Well, if we kind of look for what's happening on what's on the outer ring of this function, we've got a sine, and then a nice big set of parentheses there, and then a bunch of stuff going on inside those parentheses. So same deal as before. We're going to find our outer function first, or we want to find our outer function and our inner function. We're actually going to start with the inner function. So the inner function, we see this nice juicy set of parentheses, and it's all that stuff that's inside the parentheses. So it'll be the x to the 4th plus 9x plus 3. And so to get the outer function, You imagine just taking all that stuff we just wrote down, taking all of this, and again, collapsing that down to just a single variable. So what do we have left after we just replace that with a u? Well, that's going to be our outer function. So in this case, it'll be sine of u. All right, so that's composition. Kind of hopefully a review. But that's one way to algebraically take two functions and combine them together, and it's not just the usual addition, subtraction, multiplication, and division. It's kind of a different thing. It's a different way to combine two functions. And what we're going to want to see is there's no product rule here, really doesn't apply for these. Quotient rule doesn't really apply. The sum rule or the difference rule, they don't really apply for these because there's a different process at work here. And so the rule we're going to look at is called the chain rule. And it tells us how to differentiate a composite function when we have an outer function and an inner function. So we've got our outer function and we've got our inner function. Okay, so this is going to be the overarching derivative rule that we're going to use, and we're going to see a few special cases. So what does this rule say? How do we actually calculate the derivative of this composition? Well, we kind of have to break our way through all the different layers. So you want to think of outer layer and inner layer. Our function has a lot of different layers. We want to kind of drill our way through all the different layers. So when we start, we're going to start by differentiating the outer function. So just the outer function part, that's the first step. Differentiate the outer function, and then we'll keep our inner function exactly the same. So that's step 2. So differentiate the outer function, keep the inner function exactly the same, and then the last step is to, once we kind of break our way through that outer function, we differentiate our way through that outer function, then we can get to all the stuff that's in the middle and differentiate that. So that's the last step. So we differentiate the outer function, we keep our inner function that's being plugged in exactly the same, and then we multiply by the derivative of that inner function. Okay. So let's see this in action for a specific case. We're going to look at what we call the general power rule. So general power rule, this is just a special case of the chain rule where our power function, where our outer function is a power function, something raised to a power. Okay, so we want to differentiate here. We have this inner function u of x, and in this case, the outer function is this raised to the power r. So what does this special case of the chain rule say? Well, we start by just kind of doing our regular power rule differentiation. We bring the exponent down, put it in front. We subtract 1 in the exponent, just like regular. And then all that stuff that's inside the big set of parentheses is just going to stay the same. So what we're doing here is we're starting by differentiating the outer function. We keep our inner function exactly the same. And then we multiply the result by the derivative of that inner function. Okay. And like I said, this is a special case where the outer function is something being raised to the power r, and then we just have an inner function, kind of a general thing. We'll call it u of x. All right, so let's see this in action. Let's look at example 3. So here we're going to differentiate that function we just worked with, x to the 4th plus 9x plus 3, all raised to the power 8. So when we do this, we'll call our derivative h prime. And again, the composition that we settled on is that the outer function here was this raised to the power 8, and the inner function was all this stuff inside the parentheses. So when we differentiate this, we have to first break our way through that outer power function. So just regular power rule here. Bring down the 8. we're going to keep everything that's inside the parentheses exactly the same. So this is not going to change here. And then we subtract 1 from the exponent, just like regular power rule. So our exponent was 8, now it's going to be 7. We subtract 1. So all we've done so far, this is just the derivative of the outer function. So we've broken our way through that outer function, and now we want to get to the stuff that's inside the parentheses. So we're going to then multiply by the derivative of the inner function. So this is our general power rule. So we're starting by differentiating the outer function. We keep our inner function exactly the same, and then we're multiplying by the derivative of all that stuff that's inside the parentheses. And then we just finish it up. So this part we're done with. And then this part we just finish differentiating. So we get 4x cubed plus 9. And when we do these, we're going to, with chain rule, we're always going to be multiplying by the derivative of the inner function. And if there's more than one term here, like there is here, make sure you use parentheses. So we do need the parentheses here. Otherwise, this plus 9 wouldn't be getting multiplied. So if you left off the parentheses, that kind of 9 would be getting left out on the multiplication. All right, so this is the idea. It's differentiate the outer function and then multiply by the derivative of the inner function. So we'll see, the other special cases for trig functions and inverse trig functions and exponential and log functions. So we'll start to look at those in class. So we'll see you then. Bye-bye.